Ken Raghavan from Institute of Mathematical Sciences. He will speak on Hilbert multiplicity of points on Schubert varieties. So, Raghavan, you may begin your seminar. We may stop you once in a while if there are questions from audience.
Absolutely, that is most welcome. I'm happy to answer questions in the middle if they don't have to wait until the end. The title of the talk is Hilbert functions or multiplicities of points on Schubert varieties in the Grassmannian. Okay, so I will start with a statement of a problem, and as I mentioned in the abstract, with apologies to experts in the audience, I will recall details of Schubert varieties and Grassmannians. But at the beginning, I would like to just state the problem. So to repeat, I will recall the definitions of Schubert varieties, in fact, about what the Grassmannian is and its Schubert and its Blücher embedding slightly later in the talk. But for now, let us just state the problem. So by GDN, I denote the Grassmannian of d-dimensional linear subspaces of Cn. So the field doesn't matter. I'm just using C here for simplicity. So we fix two integers d and n throughout the talk, d less than or equal to n. And one special case of this is very familiar to us. Namely, if I put d is equal to 1, then this is just one-dimensional subspaces, linear spaces or lines in Cn, which is nothing but projective -1 space. And this, let me introduce this notation IDN. This is going to come repeatedly. These are just d element subsets of the set 1 through n. And each element of that will be denoted, we will write the d elements in increasing order. So that's indicated here. Okay. So given there is some very intimate connection between IDN and GDN. You may think of this as somehow a combinatorial Grassmannian, so to speak, the IDN as. So for an element, given an element of IDN, we will define a distinguished point, which we will denote E sub V. So I will denote V and W and sometimes theta and sigma for elements of IDN. That will be the notation. So E sub V is a distinguished point in GDN. We'll see what this point is later. And also X sub V will denote the Schubert sub variety in GDN. And for the experts, just to recall, there is a Borel orbit, Borel group action. Again, I'll recall this later on the Grassmannian. And so you take the orbit on this distinguished point, EW, and then take the closure. That's what XW will be. I should have written XV is equal to B EV X bar, but so, and let's also note that EV, this distinguished point for V, belongs to the Schubert variety corresponding to W, if and only if V less than or equal to W. What that means is the following. So V1, so we are writing V1, V2, Vd for the D elements that of 1 through n that V represents, and similarly for W. And V less than or equal to W means precisely that V1 must be less than or equal to W1, and V2 less than or equal to W2, and so on until Vd less than or equal to Wd. So to state the problem, given V less than or equal to W in IDN, so I know that I have a Schubert variety in the Grassmannian of GDN, indexed by W, and I know that this point E sub V belongs to X sub W. Find the Hilbert function, or let's say the multiplicity of the local ring of the Schubert variety at that point. Okay? And the answer must be in terms of this combinatorial data, just these D integers. V1 through Vd is a set of D integers, W1 through Wd is a set of D integers between 1 and n. And of course, V is less than or equal to W, and everything must be in terms of this combinatorial data. Let me point out right away that although this looks like I'm doing something special here, I'm not taking an arbitrary point on the Schubert variety. We will see later on that this is good enough. So this is, if we solve this problem as stated, we will know the answer to any arbitrary problem on the Schubert variety. Okay, so this is the problem, and I will come to the solution. I will talk about the solution later. Yeah. Okay, let's do an example. Since this is a commutative algebra audience, I would like to emphasize this example. So for particular values of D, N, V, and W, it's a little bit technical to exactly fix these values. So let's not worry about that. What we get is, if we take the local ring in the problem, it turns out to be just this. You take an R cross S matrix of indeterminates, adjoin those variables xij, and go modulo the t+1 cross t+1 minus of that generic matrix. And here I'm assuming 1 is less than or equal to t+1 is less than or equal to R is less than or equal to S. This is just R is less than or equal to S just for convenience. Okay, so what is the, as we, yeah, sorry about that. Maybe I'll make that slide small. I hope that's not too small. Okay, this is the ring of functions on the variety of R cross S matrices of rank at most T, because we are going modulo t+1 cross t+1 minus. Okay, and let's put R is equal to this polynomial ring on top, and I the ideal that we're going modulo. Then I is prime. This is I is radical. In fact, it's prime. Okay? And the dimension of R mod I is this number here. Okay, these numbers these facts are classical, and you can read these off from facts about Schubert varieties that I'm going to later on explain. And so, as an example of what we are talking about, the multiplicity of this ring is given by this has this formula. It is the determinant of the T cross T matrix whose ijth entry is this binomial number, binomial R plus S minus I minus J, choose R minus I. And this is due to Jambili in 1909. And so you can see that this is interesting, and this is a very special case of the problem that we are talking about. So the formulae that we will get will be generalizing this particular one, and also providing an algebraic approach to, for example, to this Jambili formula, which his methods were apparently geometric. And so in this example, I did not mention what D, N, V, and W were, but V happens to be just 1, 2, up to D, the smallest possible values for V. So suppose I take that, and then Abhyankar in 1984, starting in 1984, computed the Hilbert function of this ring R mod I. This is a graded ring, so it makes sense to talk about its Hilbert function. Abhyankar computed the Hilbert function, And Herzog-Chung in 1992 gave formulas for multiplicity. Abhyankar also did, but Herzog-Chung gave other formulas for multiplicity and computed Grosvenor basis. So in particular, they recovered this result of Jambeli, and in fact, they say in their paper that they were motivated by the fact that there is no algebraic proof of the Jambeli formula. Okay, so I put this example in just to show that the objects that we are talking about are encompass very interesting determinantal ideas. Okay, now for the next few pages, I apologize to the experts, and I'll recall facts about Grassmannian, its Spluker embedding, and details of Schubert varieties. So this Grassmannian is a non-singular projective variety. So and that's and how that is so is what I'm going to recall now. So let us think of the familiar case, Pn minus 1, which was nothing but, can you see this if I'm writing this?
Yes.
So,
yes.
Okay. So this is, thank you. This is, as we saw, this was G1n. Okay. And as we know, the one way to get Pn minus 1 is take a non-zero element, the nn tuple, such that not all of them are zero, not all the xi are zero, and identify two of them if they differ by a scalar multiple. And I write this T on the right rather than on the left, mainly because I think of T as a 1 cross 1 matrix, and since I've written an n cross 1 matrix here, sorry, I made a mistake. I should have written it as a, no, it's correct, n cross 1 matrix. This T is a 1 cross 1 matrix. I want to think of this T as a 1 cross 1 matrix. Okay, and that is relevant for what follows. Okay, so how can I think of GDN in a similar fashion? So the way to look at this column, or not all the xi being zero, is that it is it's one column of full rank. So I denote by M n cross D all n cross D matrices over complex numbers, and the zero indicates that the matrices have full rank. In other words, they have rank D. And GLD acts on the right on this n crossing, on this M n cross D zero. In the natural way, that is just manipulating just doing column operations. And how do I think of the Grassmannian? So as you can see, so just like in the projective case, if I multiply by a scalar, the line doesn't change. Similarly, if I multiply an n cross D matrix of full rank by a GLD matrix on the right, the span of those columns does not change. It still remains the same. So in that way, we can see that you can think of GDN as a quotient of this mn cross D0 by GLD on the right. Okay, so I want to now give a projective embedding of this GDN, first just as a set. Okay, so this is how to think of this. So given a matrix here, a full rank matrix of rank D of size n cross D, and V an element of IDN. So set PV of A, so I'm going to define this. This is the determinant of the D by D submatrix of A consisting of rows V1 through Vd. So remember, this has n rows. So V1 through Vd are elements, D elements between 1 and n, arranged in increasing order. So if I choose these, then I choose these rows, then I get a D by D matrix, all columns, all D columns, and these rows, then I get a D by D submatrix, and I take the determinant of that. And that I denote by PV of A. And I'll send it to this projective space, which has coordinates PV, projective coordinates PV, V belonging to IDN. These are called Fluker coordinates. And this is okay because since I'm assuming full rank, not all these determinants vanish. So I will, out of the tuple, out of the n choose D tuple that I get, at least one will be non-zero. And so this is an honest element in this, I can think of it as an element of this projective space. Okay, now I claim that this map factors through this quotient GDN. And that is because if I multiply a matrix A by an element of GLD on the right, then the corresponding Fluker coordinate, each one of them gets multiplied by determinant of G, just this scalar. Okay, so as a element of the projective space, it is not changing. It is just the coordinates, the projective coordinates are just going to get multiplied by determinant of G. So as an element of the projective space, it is not changing. So this shows that this is a this map factors through a GDN. And why is this injective? See, the projective coordinates, I claim, determine the matrix A as an element of GDN, maybe not as an element of this space, but as an element of GDN, it's determined. So here is a proof. This is elementary, and this is a sketch of proof. Suppose let's say, fix D equal to 2 and N equals to 4. And I have so what I have to show is that I have the image here in the projective space, and I want to show that determines the image. Okay, so one of the coordinates is non-zero. Okay, so choose V in IDN such that PV of A is non-zero. And suppose V is equal to 1, 2. I'm doing that case, but any other case is similar. Okay, so then A, you can multiply A by an appropriate matrix GL2 on the right, so that it has the form 1, 0, 0, 1, and so on. And this is arbitrary. I can do this. So by doing this, I'm not changing the element in GDN because I'm just multiplying by an invertible matrix on the right. And now I observe that these entries here are just, for example, this entry here, I can think of it as the determinant of the 1, 3 matrix. It's P1, 3A. But P1, 3A is fixed because the image is fixed. So that means A is determined, right? So this proves that the map is an injection. Okay. In any case, this is elementary. Okay. So let us talk about the Fluker relation. So this is an embedding, and I want to say that the image here is there are some relations that the image satisfies, and these are the Fluker relations. So there are relations among the PV Fluker coordinates that are satisfied. I should say more clearly that these are projective coordinates. On the projective space, of course, there are no relations, but on the image of the Grassmannian, there are certain relations satisfied by PV. So, for example, if I take this, just to give an illustration of this, if I take the case G, so this is case G24, okay? So I take a 4 by 2 matrix, and then I write out P12A, P13A, etc. These are just the determinants. I want you to observe the following. Suppose I say P12A is 0. Suppose this 12 is 0 and 24 is 0. Okay, 24, CDGH. this submatrix is 0. Then I claim either the second row is 0 or P14A is equal to 0. So why is that? If the second row is non-zero, if the second row is 0, I'm done, because I'm saying either the second row is 0. So if the second row is non-zero, then the first row is a multiple of that second row, right? And the fourth row is a multiple of the second row. So both those rows are multiples of this non-zero row, and therefore P14A is 0. Okay. So in particular, P23A is 0 or P14A is 0. So this is just a simple illustration to show that if these two are 0, such a relation, and this is also easy to see because you can just, I've written it out here. This is just a simple checking. Okay. So there are some relations similar to these that you can write. These are called the Plucker relations. And here is an important fact that's basic to all that we are doing. So the image in the projective space of the Grassmannian under this embedding that we have defined equals the variety defined by the vanishing of the Plucker relations. So in fact, I should say, in fact, I say that later. Okay, let me, at the bottom of the page, I say the homogeneous coordinate ring S of GDN in P in the projective space equals this polynomial ring modulo the Plucker relations. So the Plucker relations, in fact, are the ideal of relations that vanish on the image of GDN. Okay? For use at a later stage, I want to think of this relation, Plucker relation, as follows. So I want to rewrite this. I've written this, the same thing on top. I'm rewriting this, and on the left here, you see I've drawn the partial order among I to 4. These are all elements of I to 4 and their partial order. If you go to the right or go up, then those elements are bigger. So 2, 3, and 1, 4 are incomparable, but 3, 4 is bigger than 2, 4 is bigger than 2, 3, and so on. Okay. So observe that 1, 4, and 2, 3 are the incomparable pair, right? And what you're able to do is write their product as sums of products of other ones. But here, both 1, 3, 2, 4, which is this 1, 3, 2, 4, these are comparable, and 1, 2, 3, 4 are comparable. Okay, so this is going to be important. So whenever we have a product of incomparable projective Plucker coordinates, then we'll be able to write them as express them in better form. Okay, we'll see. I'll state the theorem later. Okay. So GDN, the Grassmannian, is a non-singular projective variety. In fact, GDN has a okay, why is this non-singular? GDN has a transitive action of GLN. So we took remember GDN, we realized it as a quotient of M D cross N, full rank matrices of size D cross N, and used the action on the right of GLD, but there is also an action of GLN on the left. I should say not right here, but left. Okay, left multiplication by GLN on this space is transitive, the transitive action. And since the left action by GLN and the right action by GLD commute, the action of GLN on this space goes down to the Grassmannian. Okay? And since this is a transitive action, it follows that this is a non-singular projective variety, because any variety in the classical sense has at least one non-singular point. And since this is a transitive action, every point is like every other point. So it's non-singular. Okay, now let's talk about Schubert Sub Varieties in GDN. Okay, as we observed at the very beginning, these are indexed by elements of this IDN, and the notation is X sub V. Some special cases, notable special cases. If I take it to be the smallest possible V, that is 1 through D, then this Schubert variety is just a single point. Okay? And if I take it to be the biggest possible option, namely take n to be the last element and then just n minus 1 before that and so on, the biggest possibility elements, then this Schubert variety is the whole of the Grassmannian. Okay? And it will also turn out that the Schubert variety corresponding to V is contained in Schubert variety corresponding to W if and only if V is less than or equal to W in the sense defined. That is, V1 less than or equal to W1 and ... and Vd less than or equal to Wd. Okay. Okay, so to define the Schubert variety, I'll define the following. For given x in a point in the Grassmannian, I want to define an element of IDN as follows. Okay, so what you do is you fix the standard basis of Cn and take this flag. So F1 is just the span of E1, F2 is the span of E1, E2, and Fn the span of E1 through En. Okay. So we have this, this is called a flag because the dimension of Fi is I. Okay. Yeah, note that x intersect F0. So if I start intersecting so x, remember, is a d-dimensional linear space in Cn. So I can intersect it with any other subspace. So in particular, I'll start intersecting with these Fis. And of course, if I intersect it with a zero space, I get 0. And with if I go to the Fn, then this is just the whole space Cn. So this just gives me x, so I get d. And in between, so these are linear spaces, so if I take Fi and Fi plus 1, or Fi and Fi minus 1, as I've done here, then Fi is just one dimension more than Fi minus 1. So it follows that either the dimension will remain the same or it increases by 1. Okay, so what this means is I start at 0. When I intersect with F0, I have dimension 0. When I intersect with Fn, I have dimension d. And I must increase at most in steps of 1, which means precisely there are d points, at d of these stages, I increase exactly by 1. Okay, and that is my definition of Vxt. So in other words, it's the least I such that dimension of x intersect Fi is equal to j. Okay, and now xw is defined as follows. Now we are giving the definition of the Schubert variety. It is all those points for which the IDN turns out to be less than W. Okay, and as you can see, or at least intuitively clear, that this is a closed condition. If you having more intersection, if you take, so to speak, a limit of elements x, all of which have some given intersection, the limit point either has the same intersection or even more. So this is a closed condition. Okay, so let's do this. I want to just explain this in a little more detail in one particular case, x24 in G24. So what does this mean? This means that I must hit 1, at least 1, when I reach 2, which means this is, if you unwind the definition, this just means all those two-dimensional subspaces of C4 that intersect this plane E1, E2, this is the standard basis vectors, non-trivially. Okay, so it could either be the whole E1, E2, or it could just be a line. Okay, it has to intersect it non-trivially. Okay, so using this, suppose I want to compute the dimension of x24, how do I do this? So here is an intuitive or heuristic way of doing it. So what are the conditions? it must intersect this in a line, right? Of course, it can intersect it. It could be the plane E1, E2, but that's the degenerate case. So it's not going to happen. So for a generic element of X24, it's going to intersect this only in a line. So I choose that line in F2. That F2 is this E1, E2. And how can I choose a line in F2? This is like choosing a line in 2 space. That's like P1. So it's one parameter. Okay. And having chosen that one-dimensional subspace, I must choose one other. So to get to my to my two-dimensional subspace, what must I do? I must choose one other, and that is modulo L. I must choose one more. And now this is dimension 3. So I'm choosing a line in a dimension 3 vector space, and that's that's like a P2, and so it's a dimension 2. So I get the count. This count gives me 1 plus 2 is equal to 3. So observe that 1 plus 2 you got by 2 minus 1 is 1, and 4 minus 2 is 2. And in fact, that works more generally. So you have the dimension of X sub V is V1 minus 1 plus V2 minus 2 plus Vd minus D. Okay. So remember the formula for the dimension of R mod I for the determinantal minor. So you can easily deduce that from this formula, and this itself is quite easy to see. Okay. Okay. Let's also look at this observation. This example is going to be useful. X24 has a special point, namely this plane itself. Okay, we all understand. So what are we looking at? All those subspaces which intersect this plane non-trivially. But if I take the plane itself, that is the only one which intersects it in a two-dimensional subspace, right? And that turns out to be a singularity, and that is quite intuitively quite understandable. And so if I look at this X24, so I'm going to take this P12 not equal to 0. Remember, this is a projective coordinate, Plucker coordinate on my projective space. So when I take P12 not equal to 0, I'm taking an affine subspace of that coordinate affine subspace of that projective space, and I intersect this with X24. Affine open in this projective space, as I've said. So, and it's not difficult to see that this G24 intersect this affine space is actually itself a affine space. So remember, this is of dimension 6. This projective space is of dimension 6. So this affine space in P12 not equal to 0 here is dimension 6. But here, when I intersect it with G24, it's of dimension 4. And in fact, it looks like this. The reason, so this P12 not equal to 0 corresponds precisely to this 1, 0, 0, 1 here, right? I can make that equal to the identity because I have assumed that this coordinate is non-zero. And these 4 are arbitrary. So this is in fact a affine 4 space. And what does this X24 turn out to be? It just turns out to be this condition that these 4 elements here are, this 2 by 2 submatrix here is singular. So that's if I take xy, zw as the coordinates there, then xy minus zw should be 0, and that's why it turns out to be that. And the F2, the special point, turns out to be precisely the origin. Because if I put 0, 0, 0, 0 here, then you see the span of these two is just, this is, if I take x, y, z, w all to be 0, then this is just E1, and first column is E1 and the second column is E2. So I'll get the span of those two is precisely F2. That's why F2 is the origin. And let me also explain, in order that the span of these two intersect F2 non-trivially, it is necessary and sufficient that if I multiply this by something and add it to here, and these two, the first, I must be able to kill these. Okay, and that's why this determinant is singular. Okay, so you see, this is a simple example of a singularity on a Schubert variety. X24 is a singular. X24 is a singular Schubert variety. In fact, this is its only singular point, and this is how it looks. The ring looks, and of course, now you know the multiplicities too. In this case, it's easy to see. Okay. Okay, a little more on Schubert varieties before we move on. Okay. Given V in IDN, I'm now going to define this special point EV, and that is just EV1, EVD. These are, remember, the standard basis vectors, right? So, for example, if 2, 4, then this is the, in 4-dimensional space, I would be taking the span of the E2 and E4, the second and the fourth standard basis vectors. Okay, and let's also observe the following. So if I take this space and calculate the intersections, you will see that the jumps happen precisely at V1 through Vd. Okay, that's easy to see. So by our definition, here is the definition recalled for you. EV belongs to XW if and only if V less than or equal to W. Okay. Now remember, at the beginning, I said that it is enough to look at all such points. Although I stated the problem as saying that take a general point on the Schubert variety, it is enough to choose these special points. Why is that? And here is an explanation. So let B be the upper triangular matrices with respect to the standard basis in GLN. Okay, so remember GLN is acting on the right, on the left on your Grassmannian. Observe the following. If I take an element of, and I should say here, for all B in B. So if I take an element of upper triangular element and look at and hit it with Fj, right? So it doesn't move at all, it fixes. Okay, in fact, B is the stabilizer of the entire flag. So you can say B Fj is equal to Fj for all one less than for all these J, for all B in B, and if for some element it is true that if for some element G of GLN it's true that G of Fj is equal to Fj for all J, then that such a G belongs actually to B. Okay, but okay, given this, we observe that Vbx doesn't change, and here is the explanation. So if I want to compute Bx intersect Fj, right, I want to compute those dimensions, then I can, by acting on some group element, the dimensions don't change, right? I mean, the intersections, everything works out right. So if I multiply this by a B inverse, I get X here and B inverse Fj, but B inverse Fj is Fj. So this shows that Vbx is equal to Vx. So if I multiply an element X by an element of B on the left, then its V doesn't change. Okay, and so it's from this it's easy to see that XW is nothing but the B orbit closure of the special point EW. Moreover, you can decompose this orbit closure into a disjoint union of B orbits, and this is how it's a finite union of B orbits, and this is how it looks. And so the fact that there is an action of B on XW in which in each orbit there is an element EV shows that it is enough to consider these elements EV in XW. Okay, and moreover, and this will be important for us, this shows that XW is irreducible because this is B is an affine space, or at least upper triangular invertible. So it's maybe C1 star n times and then C cross C, as many times as there are elements in the upper triangular in the upper part of the triangle of the matrix. So this is an irreducible variety, and so if its action, will be some morphic action, and therefore this is going to be this orbit is going to be an irreducible object, and its closure is also irreducible. Okay, and in fact, I don't know if I'm going to use this, but it's nice to observe that BEW is an affine space, is itself an affine space of dimension this. Okay, so BEW is nothing but an interesting compactification, so to speak, of the affine space of dimension this. Okay. So now let's start writing equations for XW, which is going to be important for us. So recall, as we saw, the equation for x24 intersect p12 not equal. So this, I look at this affine patch, so to speak, of x24, and we saw that that was that was equal to this affine variety. And what was the equation that we wrote? It's xy minus zw, right? And how did I get this xy minus zw? You can think of this xy minus zw as this p34. So if I take p34 restricted to x34, it is just this determinant. Of course, I'm here there's a mistake. It should be x24. Okay. Yeah. So this determinant is 0. I'm saying that. So in fact, p theta restricted to xw is 0 unless theta less than or equal to w. That is, if theta is not less than or equal to w, then the that Plucker coordinate vanishes on the Schubert variety. That is, it lies on that hyperplane defined by that p theta. Okay, and here is a theorem. In fact, I don't know who to attribute this to, but definitely it is. It could be Sheshadri, but possibly somebody before him. The homogeneous coordinate ring of XW is given by the following. So you take this Plucker coordinates and then go modulo the Pluckers. That will give you the Grassmannian. And in fact, if you go modulo all those p theta, cut by all the coordinate planes such that theta not less than or equal to w, and that will give you the full ideal. So XW is ideal theoretically defined by this. Okay. So as a reference to all this material, I apologize to the experts for this elementary digression. So here is some place to read about this. Sheshadri Introduction to the Theory of Standard Monomials. This was Brandeis lecture notes. Lectures that he gave at Brandeis sometime in the 1983 or so. But now they are available. They're available. Hindustan Book Agency printed them again, reprinted them, and it's called the second edition. And maybe American Math Society distributes these books in every place other than India. Okay. Okay. Any questions so far? Before now we are done with the recall, and now we really come to the crux of the matter. Jugal, can I proceed, or are there questions?
Yeah, I had a question. Can we explicitly describe the singular locus of a Schubert variety?
Yes, you can. Yeah, there are descriptions. Yes. Yes. Answer is yes. And there is a paper by, for example, Lakshmi Bai and Sheshadri in the Bulletin of the American Math Society in 1984 or 85, which does that.
Okay.
And there is also for the, not just for the Grassmannian, but for others as well. So what Lakshmi Bai Sheshadri give is a way to compute the tangent space, Zariski tangent space of the at any given point. Hello, is that how I answered that question?
Yeah.
Okay. Okay. There are other so any question about Schubert varieties? Of course, there are lots of people have worked on it. There is something called the Lakshmi Bai Santhya conjecture, which is being proved. And there are many other things about singular loci of Schubert varieties, not just in the Grassmannian, but other flag varieties. There'll be, if you try an internet search, you'll get hundreds of papers. Okay, now so let me recall now the main theorem of what is called standard monomial theory for Schubert, for the Grassmannian first, and for the Schubert variety for any Schubert variety in the Grassmannian. So this theorem is due to Hodge, and apparently it appears in his in the book by Hodge and Pedo. So the homogeneous coordinate ring S of GDN in the Plucher embedding. So remember what this is. S is those Plucher coordinates P, V, modulo the Plucher relations. This ring has a C basis consisting of standard monomials in the Plucher coordinates. Okay, so what is a standard monomial? A monomial like this in P theta is standard if theta 1 is bigger than or equal to up to theta k. Okay, that is the definition of standard. And of course, standard monomials of length k for the kth graded piece of Sk. So here, if I want the full basis for the whole ring, I must let k vary. If I keep k fixed, then I get it for the graded piece Sk. Okay. And what about the Schubert variety? So the analogous statement was for the Schubert variety was proved by Musli for sure. I don't know if somebody before him did it. Analogous statement for the Schubert variety goes as follows. You just change the definition of the standard monomial to say W dominated standard monomial. Because you see those P theta, if theta is not less than or equal to W, it's going to vanish from the Schubert variety. So this is not so unexpected. So you take those standard monomials, which are W dominated, which means the highest one is dominated by W, like so. Okay, and this theorem is the same. If you take all of them as k varies, then you will get a basis for the coordinate ring. And if you just restrict to those of the fixed length, then you will get it for a graded piece.
Raghavan?
Yes.
So I think you can ascribe this theorem, what you call Musli, and also the theorem on the previous slide, to Hodge. Hodge.
To Hodge? Okay.
Yeah. See, Musli, what he did was to take this as this and the postulation formula as a sort of starting point and prove the vanishing of this.
Okay, just one question. Yeah. Did Hodge also do the Schubert case?
Yes, very much so.
Okay.
It's in volume 2 of Hodge and Pedo's book.
Okay, sorry. Thanks, Sudhir. Yeah. Okay, so this is okay. Okay. Thanks. Okay. Okay, now let's get back to our problem. Okay, now, so I take my x in xw, want to study, so this is my Schubert variety. I take an arbitrary point and I want to study the local ring. And as I've already said, since this Schubert variety is a union of B orbits like so, may assume this x to be E sub V for V less than or equal to W. Fix this. Okay, now we are done with this. Now what I want to do is I want to concentrate around this point. So I want to move from projective geometry to affine algebra. So I can observe that this coordinate PV on this point EV is 1. So it's non-zero. Okay. So we can invert PV because I'm interested in the neighborhood of this point. So I don't need to worry about the whole of XW. I only care about neighborhoods of V, so or VV. So I can invert this PV and focus on the affine patch PV not equal to 0. So let me introduce this notation. YVW is XW, this Schubert variety, intersect on which this PV is non-zero. Okay. So this is like an affine space in the big projective variety. When I intersect it with the Grassmannian, I'll get some smaller dimensional affine space, and I'm intersecting that further with the Schubert variety. Okay. Okay. So as I've said here, this is contained in the Grassmannian, that, and this is an affine space of dimension d cross n minus d. Okay, and we'll come to the coordinates in a minute. And EV definitely belongs to this. So now we are down to affine algebra. Okay, and here is a way to coordinate this. This space comes with natural coordinates. So, for example, if I take V is equal to 2, 5, 6, and I'm in the case D equal to 3 and N equal to 7, then I have inverting PV means I have made this 2, 5, 6 determinant equal to 1, right? Okay. And then so the Grassmannian itself looks like arbitrary in the, the other coefficients, other entries can be arbitrary. And so I denote them as variables. And what are these variables? Observe that each one of them, for example, x1, 2, I can get as the determinant of the submatrix of 1, 5, and 6, right? So if I take the first, sixth, fifth, and the sixth row and take its determinant, I get 1, 2. So these elements RC are, I can think of them as P theta by PV, where theta is an element of this I and D, which differs from V by just one element. For example, here I took 1, 5, 6, which differs from 2, 5, 6 by just one element. And each time the theta differs from V by a single element, I will get one of these coordinates. Okay, and so these variables here are P theta by PV, where theta differs from V by just one element, and the notation R comma C is justified because if theta differs from V in one element, it omits an element C and it includes an element R, element C which is in V, and it includes an element R which is not in V. So I can just denote this by RC. Okay. So equations for this. So this is some singular object, in general singular object sitting in this affine space. For example, like our determinantal variety sitting inside the affine space. Okay. So what are the equations for this? Well, I mean, since I know the equations for XW were given by these P theta by PV where theta is not, sorry, P theta where theta is not less than or equal to W, it follows that YVW is just given by P theta by PV such that theta is not less than or equal to W. That's easy. The problem, however, now is that this P theta look like a very nice projective coordinate on the as a projective coordinate, it's very nice, but this F theta is a determinant, okay, and its size, so note F theta is a determinant. Its degree in the variables RC equals, and this is more or less obvious, it's the number of, it's how much theta differs from V, okay, and that I call the V degree of theta, and this F theta will be a determinant. So what we are getting, therefore, is this YVW looks like some affine, is the spectrum of some affine, if a polynomial ring, modulo certain determinants of certain crazy determinants. Okay, whatever this P theta by PV turn out to be for theta less than or equal to W, and these can be very wild. At least if you look at from this point of view, if you look at it, there seems to be no rhyme or reason why they should appear. But if you look at it from the Schubert varieties point of view, they occur, they get unified very naturally. Okay, so now I want to present maybe some. So far everything, maybe there was nothing new for the experts, but this is probably something not well known, although still quite old. So this is around 1990. Okay, this is following Lakshmi Bai Wyman. This is not the way they state it in their paper, but essentially it is their theorem. So I want to now come. So remember what I attributed to Muslin, and Sudhir corrected me, which is attributed to Hodge. For the Schubert variety, the p thetas, theta not less than or equal to w, give the define it ideal theoretically. Now for the I want to do this now for the affine patch, and here is a rather nice argument that gives it for the affine patch as well. So once again, fix v less than or equal to w, and put this yvw is equal to xw. So this is already seen. This is the affine patch. Then, so we've already seen this word, W dominated standard monomial. But now I'm introducing one more term. The V compatible W dominated standard monomials, now in these F theta, not in the P theta anymore, F theta. F theta are these, just remind you, form a C basis for this. Okay? And what does V compatible W not dominated standard monomials mean? Standard we have already seen. W dominated we have already seen. What is V compatible? It just means theta I must be comparable to V, but not equal to V. Okay? Note that if I take if theta equals V, then PV is just FV is equal to 1. So it makes sense to omit it. Okay? So the statement is that V compatible W nominated standard monomials form a basis for this ring. Okay. Okay. So let's look at the proof. I want to give you a proof of this. Okay. Suppose there exists a non-trivial linear relation among the W dominated V compatible standard monomials. Then you can just multiply by a large power of PV to clear denominators and get a non-trivial linear combination of W dominated standard monomials in P theta. Right? I am just going to multiply by PV everywhere. And since these are V compatible, if I include a V, it is not going to hurt the standardness, right? And everything is dominated by W, that continues. So I'll get a W dominated standard monomials in P theta. But this, however, vanishes on XW because this is an open set in XW and the VW. And if the original was a relation, original linear combination was a relation, and it will follow that this this linear combination that I get of the W standard monomials, when I restrict to XW, on XW, it will vanish. But that's a contradiction to linear independence in not Mussoli's theorem, but Hodge's second theorem. Okay, and the spanning also is quite easy. So enough to show that given a monomial with theta j less than or equal to W, okay, there exists H such that PV, if I take a high enough power of PV and multiply, when expressed by, again, this is by Hodge, as a linear combination of W dominated standard monomials, each term is V compatible. Okay, here it may have V in it, but in fact it does have V in it, but V compatible means sorry, I should have used some other weakly V compatible in the sense that it could be equal to V, some of the elements, but every term that occurs on the right side of the linear combination, every element that occurs is comparable to V. That's what this means. Okay. Now, this is also quite easy. So if V occurs in the original P theta 1 through theta t, then I have nothing to do because this is, okay, I can even take this to be a standard monomial, right? Because I already know that standard monomials span. I can take this to be a standard monomial and then do it, okay? So if V occurs in theta 1 through theta t, then you may take h equal to 0, because if v occurs, then already everything is comparable to v. Okay? If not, then I claim this number will suffice. H is this, t is this number of elements that you've taken, and d is this GDM, right? Okay. Then PV must occur in every term of the RHS, because in any straightening, here is the property of the straightening. So to explain this, look at this example, P1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. Observe that in every term, the thing is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 occurs, right? So more generally, of course, you can have P1, 2 into P1, 5 into P3, 4, etc. Something, some other complicated thing. But you look at all the V's that occur in every term and look at their union as a multiset. That set doesn't change. That is, if one occurs 100 times in one of these, then it will occur 100 times also in this, and 100 times here, and similarly for 2, and similarly for 3, and so on. Okay? So, given that, what you can do is, if multiplying by a huge power of V, then you're sort of increasing, you're getting more and more elements of V, right? And the theta 1 through theta t, the other elements will not suffice. If they differ from V, they will not be able to contribute enough. And so this is an elementary proof. I'm afraid I've not made it very clear, but it's elementary. So this does the job. Okay, so here is the corollary, and with this I finish today. So observe that this is graded, okay, because the f thetas were all determinants, and they were all homogeneous of the same. They were all homogeneous. So this is graded. Okay. So I was supposed to compute the associated graded of this CYW at the origin, right? Because that is the local ring. But since it's graded, then I don't have to worry about computing the associated graded. And this is crucial because if you try the same trick for something like the full flag variety, Schubert variety in the full flag variety, and then various versions of the theorems we have talked about are available, and you can try to make the same deduction. And what you will get into trouble here, because the f thetas that you get will not anymore be graded, will not be homogeneous. So this ring will not be graded, and the problem turns out very difficult, and in fact it's an open problem. So we don't know how to compute in general pass from the ring to the associated graded ring. Okay, but in this case the problem vanishes because it's already graded, therefore it's equal to the associated graded. So all we have to do is, now we are down to combinatorics. All we have to do is the following. So I just need to, I have a basis for this ring in dimension L, for example. I have to compute the W-dominated V-compatible standard monomials in f theta of degree n. It's just a combinatorial problem. The f doesn't play a role here. I just have to write all these theta 1 through theta k such that the V degree of theta 1 plus V degree of theta k is equal to L, right? And it's just a question of counting how many elements are there in this combinatorially defined set, and that will tell me the Hilbert function of this local ring evaluated at L. Okay, and so let me stop here, and next time we'll see how to solve this. Thank you.
Okay, thank you, Raghavan. We can take questions. Yeah, if you have any questions, you can unmute and ask.
Can I make a remark?
Yes, please.
I mean, Raghavan, please correct me if I'm wrong, but I think this YVW that you are looking at, so you intersect XW with EV not equal to 0, right?
Yes.
If I'm not mistaken, these are precisely determinantal varieties co-generated by a minor.
That is true if V is identity.
Uh,
Depends on what you mean by co-generated. Maybe if you enlarge the definition of co-generated, yes.
You're right. Yeah, you're right.
So usually the definition of co-generated, I think, is when V is identity, if I remember right. But
yes. Yeah, it's V is identity. That's right.
yeah. So that is the case that was done by Abhyankar and
Yes.
Herzog. Yeah. And that is good enough for the determinantal variety that there indeed V is identity. So
Right.
that is, when I say V is identity, I mean 1, 2, 3 up to D.
And what did Miller and they did something, right? This Ezra Miller with these varieties? I forgot now.
You mean Knudsen and Miller or Sturmfeld? So Sturmfeld did compute the Grobler basis for the determinantal case, the T plus 1 cross T plus 1 cross minus, I think. And maybe other things as well, but that's one thing surely Sturmfeld did.
No, Knudsen and Miller. I mean,
okay, Knudsen, Miller, yeah. So, so they talk about matrix Schubert varieties,
right?
So, and if you unwind their results enough, and this is not easy to do, you will at least get the V is equal to identity case.
Mm-hmm.
And it may be that from those results you can also get the general case, but I'm not so sure. But even relating this and that is not easy. Meaning, but you can. It is hidden there somewhere, buried there somewhere.
And you say that for the flag case, the full flag variety, this is not understood. But if you take V equal to identity, what can one say?
No, even in the case V equals identity. Yeah.
I mean, you get those. You get the ladder determinantal varieties. That's part of the.
No, that is true. In very special cases, things are known. So you're right. So if I take, I think that. As I mentioned in the abstract, but didn't mention now, although I say in general it is open, there are many special cases that are known.
Right.
And the ladder determinantal variety case would be one such special case. So in general, if I take any Schubert variety in SLN mod B or GLN mod B, and look at any point, even if it is the worst point, so to speak, the identity point, the 1 through D, the answer is not known.
Okay, any other question?
May I comment?
Yes.
The singular locus of Grassmannians and Schubert Sub Varieties written in the book of Bruns and Vetter, lecture note in mathematics, in chapter 6, I think. I can't recall the result right now, but probably it is written in that book.
Yes, likely yes, yeah. For the Grassmannian case, many different things are known, but you can ask more generally. Yeah, I can believe that. Yes, thanks.
I didn't get the reference that Miyazaki pointed out.
I think he meant Bruns and Vetter determinantal rings.
Okay.
Or is that the name of the book? Did I get it right?
Yes.
Yes, that's right.
Yeah. Okay, I don't see any further questions. So Raghavan, thank you again for the very nice introductory talk for our young researchers. And we shall again on Friday at the same time.